trig inverse functions, their derivatives. So we're stepping a little away from implicit, and we're working on derivatives of trig inverse functions. So more rules again, more rules for the derivative of trig inverse functions. So maybe what I'll do is give you the rule, practice the rule, the algebra, and cleaning it up, and then tomorrow I'll show you where some of the rules come from. So these are derivatives of trig inverse functions. We know the derivatives, I hope, of the trig functions, but now we're talking the inverse trig functions. So the first one is, if y equals sine inverse of u, what would be the derivative of that? As a rule, the derivative is y prime equals 1 over the square root of 1 minus u squared, and u is the inside stuff. So whatever this is, that's what's going there and is getting squared, and then times it by the derivative of the inside stuff. So for example, an easy example, if y equals sine inverse of x squared, y prime would be 1 over the square root of 1 minus the inside stuff squared, which is x to the fourth. Because x squared squared is x to the fourth. The derivative of the inside is what? 2x. That's the derivative of the inside. Number 2, y equals tangent inverse of u. The rule will be y prime equals 1 over the square root of 1 plus u squared, it's the inside stuff squared, times u prime, the derivative of the inside. So as an easy example, if y equals tangent inverse of root x, y prime would be 1 over 1 plus the inside stuff, which is here, and root x squared is just what? X. Times the derivative of the inside stuff, and the derivative of root x, we should know by now, is 1 over 2 root of what? X. And they don't really simplify these two. You can't do better than that. So this would be an acceptable answer. Right here. Okay? Now, the derivative, because it's hard to fit on this board, but the derivative of cosine inverse, if y equals cosine inverse of u, the derivative is the same thing as sine, except for the negative, the sine itself. So then if you know sine inverse, cosine inverse is the same thing, except it's a negative 1 over the square root of 1 minus u squared times u prime. And the same thing is true for tangent inverse. If y equals cotangent inverse of u, then y prime is 1, the negative 1, over 1 plus u squared times u prime. It's just the negative of that. It's just the negative of that. Okay? All right, so these are, again, if you know the one, you know the other. You pair up sine inverse and cosine inverse, pair up tangent inverse and cotangent inverse. So you really only have to know 3. And if you know 3, the other 3 are just the negatives of those. Okay? All right, and 2 more, the last 2. Y equals, that's 2, 3, well we did here 1, 2, 3, 4, so let's do these as 5 and 6. Y equals secant inverse of u. So what would be the derivative of secant inverse? They're nothing like your other functions, like with the secant tangent. They're nothing like that. So y prime would be equal to 1 over the absolute value of u times the square root of u squared minus 1 times u prime. It's 1 over the absolute value of the inside stuff times the square root of u squared minus 1 times u prime. So for example, if y equals secant inverse of 3x, then y prime is 1 over the absolute value of the inside stuff times the square root of the inside stuff squared, which is 9x squared minus 1, times the derivative of the inside, which is 3. And because this is just a constant inside the absolute value, you can pull this out and make it the absolute value of 3 times the absolute value of x. That is true. That the absolute value of a product is the product of the absolute values. You can split them apart. So the absolute value of 3 is 3. So these 3's would divide out, and this would now be equal to 1 over the absolute value of x times the square root of 9x squared minus 1. And like I said before, if you know secant inverse, you also know cosecant inverse. So the last one, number 6, if y equals cosecant inverse of u, then y prime would be equal to just the negative of it. Negative 1 over the absolute value of u times u squared minus 1 times u prime. It's just the negative of it. So if you know secant inverse, you know cosecant inverse. Remember, the derivative of a c function is a negative answer. And if there's time, I'll show you even where one of them comes from before it's over. But let's just practice using them in the algebra. So here we go. Suppose y equals sine inverse of 3x over 4. So, there's only really 3 to know. Let's learn these right now. There's only 3 to know. Sine inverse is what? Say it after me. 1 over the square root of 1 minus u squared times u prime. That's it. 1 over the square root of 1 minus u squared times u prime. Tangent inverse is 1 over 1 plus u squared times u prime. And then if you know tangent inverse, you automatically know which other one. Cotangent inverse is the same except it's a negative. If you know sine inverse, it's the same thing except for the what? The negative. And the last one is secant inverse. It's 1 over the absolute value of u times the square root of u squared minus 1. Okay, so what is this one? It's 1 over the square root of 1 minus the inside stuff squared. So that's this stuff. That's your u. So what is that squared? 9x squared over what? Times probably the derivative of the inside, that chain rule. What's the derivative of 3x over 4? What's the derivative of 3x over 4? Yeah, 3/4. It's the same thing as 3/4 x, right? 3/4 x, right, is the same thing as 3x over 4. So the derivative would be then what? 3 over what? 4. Now you're not done. The rest of it's all algebra. That's the derivative. It's pretty easy usually. Most people get it. I'm going to get a common denominator by turning this 1 into a what? 16 over what? 16. And by the property of square roots, look over here. The square root of a quotient, that's the square root of the quotient, is equivalent to the square root of the top over the square root of the bottom. You can split them up over products and quotients, but not sums or differences. They're not true for that. You can't split radicals up over a sum or a difference, but you can for a quotient or a product. So what I'm going to do is, I'm going to rewrite this as the square root of, combine the tops, 16 minus 9x squared over 9. And I didn't forget about the 3/4. Now what I'm going to do is I'm going to take the square root of the top and the square root of the bottom. I'm going to split that radical up. So this will now become 1 over the square root of 16 minus 9x squared over, what is the square root of 9? 3. Still times what? 3/4, yes? Now I'm going to invert and, because this is a complex fraction, it's 1 over that. Do you see that? And are you seeing again where I got the 3 from? I took this square root and broke it up. What? Oh, did I put the bottom as 9? It's 16. What's square root? I'm bad. What's square root of 16? Sorry. 4. Yeah, thank you. So it's 16. Why did I not write that? So what's square root of 16 then? 4. Right. The bottom was 16. Yes. So then now, what's the square root of 16? 4. Invert and what now? So it becomes 4 over the square root of 16 minus 9x squared times what? 3/4. And what happens to the 4's? And there's my answer. 3 over that. So yes, just be careful. I don't know why I had the 9 and 16. Correct. Okay, let's do another one. Let's do tangent inverse. Let's do y equals tangent inverse of x over 2. Try that one. There's an error there. Remember, this stuff always gets squared. Good. And don't forget to times it by the derivative of the inside stuff. Nope. I'm not sure what you're going to write next, but you can also do the squaring in your head. That's the wrong rule. There's no square root of that. Tomorrow you have to memorize the inverse rules. This way you'll know them just from memorization, the rule. There's no square root with that one. It's just 1 over 1 plus. Get a common denominator. Without it was 1 plus that. No, that's minus. Yeah, he doesn't have a book. He must have saw the one before. It's 1 over 1 plus u squared. Yeah. You may have seen that before, like merged together. So the rule is what? Y prime is 1 over 1 plus. No square root. Yes? The inside stuff squared, that's just x over 2. Squared is what though? X squared over 4 times the derivative of this, which is just 1/2 x. It's the same thing as x over 2. So that is what derivative then? 1/2. Now we got to get a common. So I'll times this by 4 over 4. So this becomes 1 over 4 plus x squared over 4. And it's a complex fraction, so we're going to invert and what then? So we'll cross it out, and this will become 4 over 4 plus x squared times 1/2. And then I can reduce it. This would become a 1, and that would become a what? A 2. Yes? So you got to get the common denominator. Remember, there is no square root with tangent inverse. That's the only one that doesn't have one. Okay, next, let's do y equals sine inverse of x over 3. Try that one now. Sine inverse of x over 3. What's square root of 9?
3.
You lost the square root there. You kind of went from having it to not having it. That should be 1 over. 1 over, yeah. You lost something there. Wait, no.
This one.
Oh, yeah, you lost it. Okay, so then y prime is 1 over the what? Square root of 1 minus the inside stuff squared, which is x over what? Times the derivative of the inside. That is just 1/3 x, and that becomes what? So what's the first issue? Knowing the rule. You got to know the rule that for sine inverse, it's 1 over the square root of 1 minus the inside stuff squared times the derivative of the inside. Get a common denominator by making this 9 over 9, and this becomes 1 over the square root of 9 minus x squared. And this is just root 9 in the bottom, agreed? Which is just what? 3. So it's 1 over the square root of 9 minus x squared divided by 3. Invert and what now? And there would be my derivative, 1 over the square root. So before we go to the board and do some practice, if I call this position, and this is in terms of time t, recall that the derivative of position is what function? Velocity, and the derivative of velocity is what? Acceleration. And we can still find tangent lines because the derivative is the slope of the tangent, right? So we can still find tangent lines by taking the derivative, evaluating it, getting the slope, and setting up the line. Okay, so let's go to the board and do some practice then.